Hi, Aniruddhan.
Hi, Boby.
So, in most of our circuits, I mean, where L, C, etc. are present, for example, current through the capacitor is C dV by
CdV
dt.
by dt.
Voltage across inductor is L Ti
Ti
by
by
dt,
dt.
and so on. So there is a derivative always.
Correct. That's true. So if you have some I of t,
Yeah,
you will have to take the derivative of that function.
correct.
Correct.
So how to deal that in the S domain?
Okay.
Or somehow we have to represent that in the.
That is true. So we actually, if you have a function f of t,
Hmm.
we need to find out the Laplace transform of the derivative of that
Derivative of
function.
that.
Oh, okay. Okay.
We'll try to express that in some equation, what you said.
Correct. Sure.
So we have f of t.
Yes.
But what we want is derivative of that,
Derivative of that.
d by dt.
D by dt. And we want the Laplace transform of
Laplace
this.
transform of this. Oh. So I want Laplace transform of, sorry, this.
Yes.
You are making my life complicated. But this may
Yes.
simplify the life later.
Correct.
Okay.
It will.
Okay.
So I think we should just start from first principles, no?
We should. So our equation is 0 minus 2 infinite d by dt of
F of t
f of t
times e power minus st dt.
dt.
Yes.
Okay. Oh,
Okay.
there is,
So you have the derivative of one function
yeah.
times e power minus st, and then you are taking.
This integration is not that straightforward.
It's not easy, right? It's not.
Shall
easy.
we use this uv or something?
Okay. I remember this.
So what was that? It is uv
Correct.
minus integral
v
du.
du. Correct.
Oh.
Correct.
So which one we will take it as?
So
We'll try something.
we'll try something. Yes.
So let's say this is u.
Correct. Okay.
And, dv is this one.
dv is that one. Yes. Okay. So then, so integral u dv is uv minus integral v du.
Yeah.
So,
So if dv is this, v will be f of t.
f of t itself, correct. Yes.
And integral v du.
V is f of t again.
Oh, so it looks.
Du is okay.
Yeah.
It seems
Seems we are somewhere close to
correct.
a doable situation.
do
Let's
it.
try.
Yes.
So u is e power minus st.
U is e power minus st times f of t.
V is f of t.
Yes.
Then I need to apply the limit.
Correct.
0 minus 2 plus infinite
Correct.
minus
Correct.
integral 0 minus 2 infinity v du. V is f of t.
Correct. So f of t du. So u is e power minus st.
Yeah.
So du will be
Derivative of.
derivative of e power
So
minus
that means
st
minus s.
minus s. Correct. Minus s
E
e
power
power minus st
dt.
dt. Correct.
Okay. So maybe I will apply the limit for this.
Yes.
At least some portion we can clear.
Correct. We can clear it up. Okay.
So e power
Minus infinity is 0.
goes to 0.
Correct.
So that goes.
Yes.
Then we have e power 0,
That is 1.
1 and t equal to 0 at t equal to 0.
So that is just f of 0.
So
But it comes with a negative sign.
correct.
Right? Okay.
So minus
f of 0.
f of 0.
Correct.
Nice.
Correct.
Then this s I can take outside, because
Correct.
we are integrating with respect to time.
Correct.
So S of,
And then I think you have a negative sign and another negative sign.
yeah, so
will
that
become
becomes
positive.
positive.
Correct.
Perfect. 0 minus 2 infinity
Correct.
f of t
Oh.
e power. What happened?
No, I can see. So this is just the Laplace transform of f of t,
Oh, ho, 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 ho.
right?
Oh,
This is the very familiar thing now.
okay, okay, okay. So what you're saying is this is
Laplace transform of f of t.
L of
So f of s.
f of t.
So this is the same as f of s. Capital F of s.
Uh-huh.
Okay.
So okay, this is nice. So that is, I just have to do S f of s
Correct.
and subtract f of 0 minus. Huh?
Correct. F of 0 minus. Correct. Oh, this is nice. So if I want to take the Laplace transform of the derivative of some function, I just have to take the Laplace transform of the original function, multiply by s,
Yes.
and then subtract out the time domain, initial value of the time domain function.
Exactly.
Oh,
So
very
the inductor you were talking of,
Yes.
at 0 minus, it may have some current flowing, correct?
Yes.
So
correct.
some initial condition
Some
could
initial
be,
condition will be
so
there.
that is already taken care. We don't have to
We don't
think
have to worry
it.
about it. Oh, nice.
Oh, this is actually very
Very useful, I'm sure.
becoming powerful.
Correct.
Huh?
Correct. Yes. This is now this. It looks like this Laplace transform is much more powerful than log anti-log. We
Correct,
took that
correct,
as a
correct,
simple
correct,
example,
correct,
but now
correct.
it looks very, very useful.
Correct, correct.
So something like differentiation has just become like a multiplying with s,
Yes, yes.
right? So okay,
That's really nice. Very good observation. Okay, so since we know this much, maybe we should try some real circuit.
let's do it. Let's build
Yeah.
a circuit
Yeah.
and
Yes. So I have some.
so since you talked about inductors, no, let's do an
Inductor only.
Inductor, but let's add at least a resistance in series with it, no?
Correct.
So
So let's say I have a source.
okay,
We'll do step,
Huh,
not sine
sure,
wave.
correct.
'Cause-
Well, let's do a step.
Yeah. So let's say u of t, maybe some 3u of t.
3u of t. Okay, fine.
A step with a height of
Sure.
3. Then inductor and a resistor. Huh?
Let's add a resistor.
Okay, so let's say this is 2 Henry and 4 ohm. And there is some current flow, I
Sure.
or I of t. Oh, now I mean we are talking about some circuit that we want to represent in S domain.
S domain. Correct.
So that means, but I'm not very comfortable. I mean, I know how to, deal with this.
Yes.
Actually, that's all I know.
That's all we know, right? So maybe we'll write down the equation in the time domain,
The differential equation.
the differential equation. That will help us, I think.
Okay. Because that we were earlier, I mean, we know how to deal with
We know how
that.
to deal with it.
Okay. Should we keep some initial condition also for?
Sure.
Because our powerful
Technique also
yes.
handles that, no?
So let's say I of
0 minus.
0 minus is some 5 amperes.
Some 5 amperes. Okay, sure. Sure.
Yeah. So keeping this, we'll start writing our
Correct.
differential equation. Differential equation. So we'll use KCL.
Sure. Let's use
Or KVL.
Yeah, KVL.
KVL.
Because we have a loop, we'll use KVL.
So what we're saying is the voltage across the inductor is L di by dt.
Correct. So 2
So
di.
2 di by dt
Okay.
plus
4i
4i
should be equal to the voltage
equal
source.
to 3 u of t.
Yes.
So, okay.
So how do you use Laplace transforms to solve this?
U of t we know how to convert.
Correct.
So let me do that first.
Okay. So what you are saying is you are going to take the Laplace transform of both sides.
Yeah.
Huh?
Yeah.
Left side Laplace transform, right side Laplace transform.
Yeah.
Solve it, and then take the
come
inverse,
back to
come back to the time domain.
Yeah.
Understood. So this is like again
Logarithm. Yeah.
I am understanding.
Correct.
Now you want to multiply two numbers, you take the log, add
Add.
them, and then do antilog.
Correct.
Okay, perfect. Let's do it.
So we have an equation here. We are trying to represent that in
Laplace domain.
Laplace domain. 3 u of t we know how
Yes.
to. So that will be 3 by
3 by s.
Yes.
Correct. Because u of t is 1 over s.
Correct.
Yes.
4i is also straightforward.
It's just 4 capital I.
Yeah.
Capital I of s.
So 4i of s.
Yes.
Okay.
So I think we should tell the students that normally in the time domain they are all small lowercase letters.
Yeah.
And in the Laplace domain you use capital letters by convention.
Yes.
So small v of t will become capital V of s.
Exactly.
Small I of t will become capital I of s, and so on.
Yes.
Okay, perfect. I think that's what you had written, small f of t and capital F of s. Perfect.
Nice. So now we need to deal with this.
Okay. So this should be.
So let's see what we have done just before.
Yes.
So what we said, if you have derivative of I,
Correct.
so it was just s f of s minus f of 0.
F of 0. Okay.
So we should be able to do that.
Yes.
So I have 2, that's common. Then I have s I of s
Correct.
minus f of 0.
Correct. So small I of 0 minus.
0
Minus. Correct. Yes.
So we have just used this.
We have just used that.
Oh, is that easy? Anything
Yes.
wrong?
No, nothing. This looks perfect.
So we'll just, this value we know anyway.
Yes.
So
correct.
we can,
just do that.
yeah. So maybe I of s will take outside.
Yes.
So I have I of s. This is
So 2s
2s
plus 4
equal to 3 by s, and here we had 5.
5.
This is 5.
Correct. So you had 2 times 5 minus 10 on the left side, so plus 10
Plus
on
10.
the right side. Correct. Yes.
Also, this means now I can get an expression for is.
Yes.
3 by s plus 10 by 2s plus 4.
Okay.
So from here, we were looking at what is I of t, correct?
Correct. Correct. So we need to take the inverse Laplace.
Yes.
Oh, this is complicated. We have
Yeah.
never.
Yeah. So we have to do that integration from c minus j infinity.
I know,
to,
correct,
or
correct.
is there any easier way? We'll try to
Let's try to rewrite it
rewrite it.
in some easy form.
So this we can write it as 3 by s by this plus 10 by.
Correct. Correct.
So 3 by s, that will become 1.5
correct. By s into s plus 2.
into s plus 2 plus
5 by s plus 2.
s plus 2.
Okay.
Okay, this looks better.
Yes, definitely. Definitely. Oh,
Yeah.
okay. 1 e power a t gave 1 by s minus a.
So e power a t
gave a Laplace transform, had a Laplace transform of 1 by s minus a.
s minus a. So we should be able to use that
Correct.
here.
Because a is minus 2. So we'll
this will
give you
be
1 by s plus 2
So this will be e power minus 2t.
minus 2t
Okay.
times 5 in the numerator. So 5 e power minus 2t
So this is that we can do.
that we can do. Okay, what to do about this? We have a second order, no? So we have a s square plus 2s in the denominator.
Oh. We will deal that separately.
Yes, let's take only the first
Yeah.
and do it separately.
So I have 1.5 by s into s plus 2. This I don't know. Because if it was 1.5 by s plus 2, we could have,
We could have done it easily. We also know 1.5 by s.
That also we know.
That also we know.
So do you want to write it in that form?
We should write it in that form. There is a partial fractions method.
Uh-huh.
We should just use that.
Oh. So that is like maybe a1 by s plus a2 by
correct s,
S
plus
plus
2,
2.
something like this. Correct.
Oh. So there will be some a1 and a2 that satisfies this.
There will be some a1
I mean,
and
if
a2
you write
that
the equations
satisfy
and
this.
then it should be
Correct.
possible to
So
find
normally what I do is I cross multiply like this and I equate the numerator. Denominator will just become s into s plus 2.
Correct.
For the numerator, for each one I would just set the other one to 0, I would get the value.
Oh.
Right? Something like that.
I'll copy to the next page.
Yes. Let's copy this to the next page and do it.
So let's find out one by one maybe.
Yes.
You were too fast, so I missed that. So what you're saying is we want to find out a1 first.
Yes. Correct.
How to do this? So what you're saying is a1 will be
Correct.
this 1.5 by s into s plus 2. I will keep s equal to 0
0.
and
Hide that part. That's very important.
Okay.
Without doing that, you can't set s equal to 0. Correct.
So this is then
1.5 by 2.
oh, that's 0.75.
0.75. Correct.
Oh, it's that easier.
That easy. Okay.
Uh-huh.
This is very straightforward.
Then a2 is again 1.5 by s into s plus 2.
Correct.
S equal to
Minus
2.
Correct. And then I have to hide s plus 2.
Hide this portion.
Correct.
So that is just minus 0.75.
Minus 0.75. That's true.
So if I plug in these values, it should satisfy.
It should. And I can see that it seems to be, no? A1 is 0.75 into s plus 2. And this is giving minus 0.5 into s. When they get added, the s term will go.
Numerator
will only be 1.5.
Anyway.
7.75 plus 0.75.
Okay. So it's working.
It's working.
Nice. So then I will bring in the full equation.
Yes, let us just write it as the full.
So the f of s what we have is 0.75 by s minus 0.75 by s plus 2.
Yes.
Oh, then we
And
heard
then the
something in
last
the
one.
previous. 5 by s plus 2.
Correct. And this is capital I of s.
Oh.
Yes. Now,
Also this we can.
correct. We can make that this thing, no?
Yeah.
4.25 by s plus 2.
Okay. So we have 0.75 by s plus 4.25 by s plus 2. Okay, now this is easy to deal.
Correct.
Because this is 1 by s is u of t.
U of t.
Hey, this is very nice here.
This is like, it's become so easy, no?
Yeah.
Okay.
0.75
So this will be small I of t.
u of t.
Correct. So left hand side, you're taking the inverse transform.
Correct.
No, this is correct.
So I will write.
So you can just left hand, you just write I of t here. And now you can write u of t here.
Yeah.
1 over
or
s
u of t we can write common also. No?
U of t you can write common also. Correct.
Or this may be less confusing.
Correct.
What you said may be less confusing. I have one term like this.
Yes.
Then
The other term is 4.25.
4.25
S plus 2. It needs to be multiplied with e power minus 2t.
minus 2t. So
Times u of t again.
So that you are saying from
This
one.
Correct. So correct. So we'll have a u of t.
Because all this starts from time
T equal to 0. Correct.
So what it means is you have some current 0.75 going always.
Always correct. At any positive time.
Positive
Correct.
time.
Correct.
Then there is some term. It starts with value and then it exponentially reduces.
It exponentially reduces. Is it because of that initial condition?
Okay.
Because
if that was not there,
actually let us see what happens if that was not there. If I of 0 minus was 0,
then this 10 would not have been there.
Then it will be very easy.
Yeah. Correct.
Right? If this 10 were not there,
Yeah.
then you would have just had
Correct. Anyway, this exponential portion, etc., are automatically taken care. I don't have to break my
You
head.
don't have to, correct. That's right.
Oh, this is very good. So my next question is, this is nice. I got I of t, I'm very happy.
Yes.
But do I have to write this differential equation always?
Maybe not, no. What you can do, it looks like the inductor can be replaced by,
Oh, then,
right?
then
Maybe we should come up with a way to write it systematically.
Correct.
Let's just do it like that.
Correct. So what you're saying is, voltage across the inductor, this V of t
V of t.
is L di by dt.
Correct.
So V of S
Capital V of S
will be L
times S times I of S.
S times I of S
Okay.
minus
F of I of 0, small I of 0 minus.
minus.
Correct. Correct. Okay.
What this means? So if I have an inductor,
Yes,
let's
correct.
go
Let's-
practical.
Let's do that.
So I have this not very nice inductor, but anyway, let's say there is current I of t flowing, and across this I have V of t
Correct.
in time domain. As per this equation, I could represent this in S domain
Correct.
somehow.
Somehow, so you'll have I of S flowing through the inductor. V of S will be the voltage across the inductor.
So
Okay.
I have the inductor. That much is easy.
Correct.
So you are saying there is a current I of S going.
I of S going. Capital I of S.
Okay, that's also good.
Okay.
And voltage across the inductor, there is, what is this? LS,
LS.
and then you have L I of
I
0
of
minus.
0 minus. Okay.
So what we are saying is I of 0 minus is the initial condition.
Is the initial condition. That's fixed also.
Correct. So that multiplied by L,
Correct.
that much DC voltage will
DC voltage is
be.
there.
A voltage will be.
Correct. Correct.
So I'll represent as a voltage.
As a voltage. Correct. So we'll do each one separately. One is the inductor.
Yeah.
The other is the initial condition.
Correct.
As a voltage. Perfect.
So this will be minus
L.
L I of 0 minus.
Yes.
So if there is no initial condition, this guy will not be
This
there.
guy will not be there. Correct.
And inductor, what shall I write? Is it just
S
Just,
times L, no?
L or
Huh? Looks like there is an S also.
okay, this is there.
Correct.
SL.
Yes, you should never forget that. It is S times L, right?
It's something similar to I mean, react.
Yes.
Huh?
In phasors,
We had omega L.
correct, we had omega L. So here it is S times L.
Easy to
Correct.
remember.
So it was in complex domain it was J omega L.
Correct.
So here we have SL. Oh, perfect. Okay. This is easy to remember.
So, shall we place this instead of our differential equation?
And just solve the equation directly.
Yeah.
Okay. Let's do that. For the resistor, there is no problem.
Resistor anyway,
I of t
there is
is
no
R
differentiation
times,
involved.
there is no differentiation involved. So, V of S will just be R times a capital I of S.
Yes.
That's all.
Yes.
Okay.
Let me copy the circuit, otherwise. So, this is what I have in time domain. What you are saying is, I can, this also we have to replace, no? The
Correct.
voltage
The
source.
source will become 3 by S, no?
3 by S. Okay. Then inductor.
Correct. So, that will become SL.
SL.
Yes. In this case, it's 2S.
2S. Then I need to add something else here, no? As per this,
Yes. Correct.
a voltage source,
Voltage source.
which is minus L I0.
Minus L times I of 0 minus.
So minus L I of 0 minus,
Correct.
which is minus 2 I of 0 is 5.
5.
Minus 10 volt.
Minus 10 volts.
Okay. Okay.
Yeah.
Volts. Yeah.
Correct. With volts. Correct.
Then resistor you said I can just place as it is.
As it is.
4 ohm.
4 ohms.
And now you have
We can just do KVL, KCL in the Laplace domain.
I of S flow. Oh, so this entire circuit now you have represented
In the Laplace domain.
So let's try I of S is equal to 3 by S minus 4 plus, because I have minus, this is a negative
Minus
voltage.
10. So plus 10.
Plus 10.
Correct. This is the total voltage. In the,
Voltage.
correct. You divide that by the total impedance. Can I call this impedance now in the Laplace domain? Because we called it impedance.
Yeah.
We had a real part and imaginary part.
Correct.
R plus j omega L, R plus jx.
Yeah.
So here,
We can call, no?
we can call it.
Yeah.
So it will just be R plus SL.
So that is,
So 4 plus 2S.
yes. So 2S plus 4.
Yes.
Is it same as what we had earlier?
Let's check. I think so. The previous page, I think one more. Yes, it is. Perfect.
Okay. Yeah, it's matching.
Perfect.
Okay.
Excellent. So now we have a more general way of doing it. Looks like. So every inductor in the time domain is replaced by SL minus L times I of 0 minus. So inductance SL, series voltage source minus L0 minus.
This is what you are saying.
That is what I'm saying.
Mm-hmm.
And you take the Laplace transform of whatever the voltage source you have. Resistance becomes resistance. You can solve the network. For
So
any
if
inductor.
this was a sine wave, then you would have used,
Correct.
we had some omega by,
Yes. For the sinusoid, it was omega by s squared plus omega squared. Cosine, it was s by s squared plus omega squared. Correct. We could have just replaced that source input by that. Correct.
Oh, now it is becoming very easy.
Very easy, correct.
And from here, of course, as we have done, we can do the partial fraction and get
Perfect.
the solution.
Correct.
Because that step is same as what you have done. Yeah.
Correct.
Oh, this is quite
That's
very
quite
useful.
good.
Very useful.
So we didn't have to solve any differential equation.
Yeah.
That is what.
Also,
is
this is
amazing.
what initially you were saying.
Yes, we wanted.
It's only
to,
algebra.
It's only algebra.
If I know addition, subtraction, division,
Correct.
I'm done with it.
You're done with it. It's very
Great.
easy. All you need to know, you find the final value in the S domain, inverse Laplace.
Yes.
Yes. It's very easy.
So if you know the transforms,
Correct.
easy to transform in both directions.
That's correct.
Yeah.
So Bobby, we have done a circuit with resistor and inductor.
Correct.
What happens to a capacitor?
Oh. Also, yeah, correct. That also has some C dV by dt.
That's right. Because the first, when we started this discussion a few days ago, the first circuit we looked at was, I think you drew RC, R1C1,
Correct.
R2C2,
Correct.
R3C3
So finally, we should be able to solve something like
for
that.
capacitor also.
Correct. So let's see. So the current through the capacitor is, I just write I
Yes,
C dV by dt.
correct.
So we should be able to use the same trick.
Correct.
Hmm?
Correct.
So I of s is C.
So d by dt is a multiplication by an s.
Yeah. So that is C is common.
C is common. Correct.
S V of s.
S v of s. And then you'll again get the initial condition, right?
Yeah. So that will be V of
Minus v of 0 minus.
0 minus.
Okay, okay. Correct. Correct.
That's all.
That's all. Oh, this is so simple. Okay.
Oh, I thought life will be more tougher.
Okay.
This is easy only.
Maybe we can just draw.
Yeah.
The-
So how will I draw? For the inductor,
We
we
did this.
had something like this. So we should get something like this.
Correct.
But here it is current.
Current is related to the voltage.
Yeah.
So you'll get a current source.
Because this seems there are two currents.
Correct.
I mean, as per this.
That's right.
Hmm?
So it will be, you're subtracting the current, so or adding the currents as the case may be.
Hmm.
So you'll get a current source in parallel with the capacitance in the Laplace domain. Maybe we'll show it.
Okay. Anyway, first I will draw the current source.
Correct.
Because C into V of 0.
Correct. Correct.
Yeah, 0 minus. That is minus.
Correct.
Correct, no?
Correct.
Okay.
So minus C into V of 0 minus
Will be this source.
will be the source, current source.
So the other part of the current is this.
Correct. So C times S into V of S, and you are adding the two.
Oh,
So they have to be in parallel, no?
okay.
Because only if you have parallel branches, currents
I
will add.
can, okay, understood.
In the case of the inductor, we were relating the voltage to the
Voltage,
current.
so it was
so
coming
it-
series.
coming in series. It is a voltage source in series. Here is a current source in parallel.
So I of s is here.
Correct.
And C,
C times S.
yes.
Correct.
And the voltage across this will be V of s. Across the capacitor.
Correct. Correct.
That's it.
Mm,
Anything wrong?
correct. No, that's okay. Correct.
Hmm.
So you'll have C times S. So I of S will be C times S into V of S.
Yeah.
Correct?
Hmm.
So that's what we are saying. And then minus C times
Initial
V of
condition
0.
also.
Correct. Correct. That's right.
Can be represented. See, this was
Very nice, no?
This was more easy to visualize.
Correct. Correct.
So we can use our
And this is also the impedance, no?
correct.
So there S times C is I by V.
Hmm.
So if you want to, so that will be the admittance.
Ah,
So we should also remember that. So the C times S
yeah.
is the admittance. So it is I of S by V of S.
Okay.
So let us say the capacitor had no initial charge.
Hmm.
So no V of 0 minus.
Hmm.
It looks like,
So what you're saying is this is admittance.
this is the admittance.
Y of S.
Y of S. Correct.
Okay. So if it is Z of S, I should have written 1 by CS.
1 by CS. Correct.
Okay. So that's why you were thinking,
I was thinking something
because it's not matching with 1 by omega.
1 by omega
C.
j omega c. That's right.
Correct. So shall we represent this in
series
form also?
Correct.
So that means I into this.
Correct. Source transformation.
Yeah, source transformation.
Yes.
So basically we'll have a voltage source
Correct.
and then capacitor in series.
Correct. And the capacitor impedance is 1 over SC.
1 by CS.
Correct.
And the
voltage source value is this current is flowing downwards.
Yeah.
So the polarity will be minus on top, plus on bottom.
Yeah.
And the value would be
The
1
same.
by CS times minus CV0. Correct. You have to multiply that current by the impedance.
Correct. So what I have voltage, sorry, current is
Current
C. I will go step by step.
Correct.
So this is
That is the current.
multiply by impedance.
Impedance. Correct. By CS. Correct.
Okay. So C will get cancelled.
Correct.
V of 0 minus by S.
Correct.
There is a minus symbol also.
Correct.
So V of 0 is actually, if it's a DC value, then its Laplace transform is like U of t 1 by S. U of t is giving 1 by S. So
Correct.
it's the DC voltage by S.
DC voltage by S. Correct.
Okay. So I can replace, if you have a capacitor in the circuit, I can replace with,
That's right.
This.
With this in the Laplace domain. With either of these two, but probably this is more useful, no?
Yeah.
So the series voltage.
yeah, depending on the other parts of the
The other
circuit.
parts of the circuits. So both of them are useful.
Cool.
So now the students should be able to solve more complicated circuits. Maybe what they should do first, that RC,
Mhm.
which you gave at the beginning,
Hmm.
maybe students can try solving it.
Or
It's
maybe,
very hard.
maybe with just 2 RCs.
Just
That's
2
also-
RCs. That is easier.
or 1 RC first and then 2
Correct.
RCs.
Correct. That's right.
Yeah.